Imagine that Mars has been inhabited by humans for 10,000 years. The first landing would now be more distant from that civilization than the earliest cities on Earth are from us, and generations of engineering would have had an extraordinary amount of time to improve the way people live there. Settlements could stretch across regions the first crews could barely reach. Farms might produce most of their food locally, while Martian ice supplies water, oxygen and fuel. People could spend longer periods outside beneath better protection, and industries built from local materials might reduce much of the dependence on Earth. But even after 10,000 years, a child born on Mars might still be unable to step outside and breathe freely. That possibility is important because becoming extremely good at living on Mars is not the same thing as turning Mars into another Earth. Human settlements could become larger, safer, and increasingly self-sufficient, while the planet outside remains fundamentally hostile to an unprotected human body. 10,000 years sounds like enough time to change almost anything, which is why terraforming Mars can seem plausible when we think on that scale. Increase the atmospheric pressure, warm the surface, make liquid water more common, and allow generation after generation to continue improving what came before. The problem is that Mars does not have one condition waiting to be fixed. A thicker atmosphere would not automatically make it breathable. Warmer temperatures would not guarantee stable water across the surface, and improving conditions in one region would not necessarily make the rest of the planet suitable for human life. Each advance could make Mars easier to inhabit while leaving other limits untouched. So rather than imagining one moment when terraforming is finally complete, a more realistic future may be one in which generations steadily enlarge the parts of Mars where humans can live with less protection. One century might bring larger enclosed settlements. Another could make agriculture easier, and later generations might inherit entire regions that feel far less hostile than anything available to the first settlers. After 10,000 years, Mars could therefore support a large and mature human civilization while still remaining recognizably Mars. So the question is not simply whether humans could terraform the planet given enough time. It is how far thousands of years of settlement and engineering could realistically change Mars, which limits might remain, and whether there is a point beyond which the planet simply cannot be made Earth-like. By the end of this video, you will understand what parts of Mars could plausibly be changed over very long timescales, what the harder limits are, and what human life there might look like if Mars never becomes a second Earth. If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. Mars gives us good reasons to think it once offered a kinder surface than the one we see today. Across the planet, dry channels cut through rock. Some join broad valleys, while others spread into shapes like river deltas. These aren't marks left by a passing frost. They record water moving across the ground, carrying sand and mud, then leaving that material behind. NASA's Mariner 9 spacecraft saw great networks of dried valleys in 1971. Decades later, the Curiosity rover reached Gale Crater and found rounded pebbles pressed into ancient rock. Their edges had been worn down as they rolled through flowing water. Curiosity also crossed layers of sediment formed where streams once entered a lake. A lake on Mars is more than a pleasing idea. The rocks remember it. Mars also seems to have had a thicker atmosphere. Liquid water cannot remain exposed for long under the thin air and low pressure found there now. It tends to freeze, boil away, or pass into vapor. Yet rivers and lakes need time to shape valleys and build layers of sediment. However warm or cold ancient Mars was, its surface conditions differed from those outside the rover tonight. That makes the first hope feel fair. If Mars lost rivers, perhaps we could restore them. If its sky became thin, perhaps the old atmosphere is still there, locked in the soil or frozen at the poles, waiting to be released. Terraforming can sound less like creating a new planet, and more like repairing one that has fallen into disuse. There's a human appeal in that thought. We know how to refill a drained reservoir and bring water through a dry canal. Mars shows us empty channels large enough to invite the same response. The planet seems to contain its own instructions. Add air, warm the ground, let the water return. The evidence supports the first part of that story. Mars changed. Water once moved across places that are dry now, and the air above them was probably denser than it is today. Neither claim depends on wishful thinking. Spacecraft images, rover measurements, and the chemistry of ancient rocks all point that way. What they don't tell us yet is where the lost atmosphere went. A vanished river leaves a channel behind, but a vanished sky does not leave a labelled tank. Some of its material may remain on Mars, and some may have escaped into space over immense stretches of time. Knowing the planet once had more air is not the same as knowing that air can be recovered. Before Mars can inherit rivers again, how much of its former sky is still within reach? For people living on Mars, the past would have no value unless some part of it could still be reached. Ancient air trapped deep inside rock might tell a wonderful story, yet remain almost impossible to recover. A buried deposit could be real and still be too thin, too scattered, or too far down to help anyone warm the planet. That changes what we mean when we call something a resource. Its presence is only the first test. Descendants would also need to find it, dig it out, separate it from the surrounding material, and move it where they could use it. Each step would require machines, replacement parts, and years of work in a place where every outdoor job begins inside a pressure suit. Mars does hold carbon dioxide in its thin air, its polar ice, and some minerals near the surface. Other gases may be locked into rocks or hidden below ground. Orbiters can map broad deposits, while landers and rovers can inspect small patches closely. Yet neither view gives engineers a simple warehouse list. Much of the planet remains poorly sampled, especially beneath the surface, and a promising signal from orbit may turn out to be a light coating spread across a huge area. Quantity makes the problem harder. A machine can collect a useful gas from a rich pocket without much waste. Give the same machine a weak trace mixed through billions of tons of dust and stone, and most of its effort goes into handling material that won't become air. The useful part may exist, but it doesn't follow that industry can gather enough of it within decades or even centuries. This is why estimates of Mars's hidden supplies can disagree without either side being careless. Researchers must infer what lies underground from surface chemistry, impact craters, radar readings, and the way minerals formed long ago. Those clues can show that a substance is present. They're less certain about how concentrated it is, how deep it lies, and whether a future mine could extract it faster than the settlement consumes energy and equipment, with no steady supply line from Earth. A terraforming plan, therefore, begins less like restoring an ancient planet, and more like taking inventory after a very long abandonment. The shelves may still hold something. Some containers may be empty, and others may be sealed so tightly that opening them costs more than their contents can provide. Past climate tells descendants what Mars once managed to hold. Present geology tells them what they might actually use. And once they know what can be reached, they face the next limit. How much machinery and energy would it take to turn that buried material into a working atmosphere? Mars can keep a record long after it loses the thing being recorded. Dry channels can remain after the water is gone. Minerals can hold chemical signs of lakes that vanished billions of years ago, while layers of rock preserve the effects of an atmosphere that no longer presses against the ground. The evidence can be strong enough to settle an argument about the past without offering much help in the present. That difference is easy to miss because a geological trace can look like a leftover supply. If water shaped a valley, some water may still be stored nearby. If a thicker atmosphere altered the rocks, some of its gases may still be trapped in them. Yet the trace does not tell you that enough material survived, that it sits in one reachable place, or that a settlement can release it without spending more than it gains. You can see the same problem in a burned house. The marks on the walls may show where furniture stood and how people used the rooms. But those marks are not spare chairs waiting to be carried outside. They are evidence of what was there. Mars has kept many such marks with remarkable clarity because its surface changes slowly in places. But preservation of the record is not preservation of the original contents. For descendants trying to rebuild a climate, that becomes a rather awkward inheritance. Their ancestors on Earth could point to ancient riverbeds and lake deposits as proof that Mars once supported conditions far milder than the ones outside the habitat door. The descendants could agree with every word, step onto the same ground, and still find almost none of that former abundance ready for use. A true history does not become a full warehouse simply because the evidence is convincing. This also changes what ancient habitability can promise. It shows that Mars was capable of different conditions when the planet had a different atmosphere, a different flow of water, and more of its early heat. It does not show that those conditions can be restored from what remains near the surface now. Time has had billions of years to move material, bind it into minerals, bury it, or let it escape to space. Mars remembers the result more easily than it preserves the ingredients. So the first chapter of terraforming ends with a smaller planet than the one the rocks describe. The past may have been wet, and the air may have been thick enough to help water remain on the surface. But any future settlement inherits the thin atmosphere that survived. The gas expected to be the easiest starting point is carbon dioxide, already present in the air, frost, and ground. If even that stock is scarce, how much carbon dioxide can Mars actually provide? Modern Mars has an atmosphere, but standing beneath it would not feel like standing beneath a thinner version of Earth's sky. At the surface, the average pressure is about 6.1 millibars, and that is around 0.6% of the pressure surrounding you at sea level on Earth. Mars is far closer to an airless world than to a world with a usable blanket of gas. Pressure comes from the weight of everything in the atmosphere above you. On Earth, that weight presses against your skin, fills your lungs when you breathe, and helps liquid water remain stable at the surface. We rarely notice it because our bodies developed inside it. On Mars, nearly all of that weight is missing. Carbon dioxide hangs overhead, yet there is so little gas that it barely pushes down. You would see the effects everywhere. Liquid water exposed to such low pressure is unstable. Depending on its temperature, it may freeze, evaporate, or begin boiling without becoming hot. A sunny afternoon can warm the ground, while the air above remains unable to hold or spread much of that warmth. Once sunlight fades, heat can leave quickly because there is very little air to slow its escape. A person outside would need a pressure suit, not merely an oxygen mask. Breathable gas would solve only part of the problem, since the body also needs enough pressure for the lungs and fluids to function safely. The suit would have to carry that pressure with you, making a small Earth-like space against the near vacuum outside. A greenhouse would face the same demand on a larger scale. Its walls would need to hold an artificial atmosphere against an exterior offering almost no support. A leak would not be a slow exchange with thinner air. Gas inside would rush toward the low pressure outside, taking warmth and usable atmosphere with it. Even growing a plant means first building and maintaining a pressurized room. This is the baseline for any attempt to warm Mars with greenhouse gases. The project cannot take a modest atmosphere and adjust its mixture until the planet becomes comfortable. It must find enough material to build a much larger atmosphere, release it, and then keep it aloft while soil, rocks, polar caps, and space continue pulling at it. Carbon dioxide already on Mars may help, but the present sky is not a large reservoir waiting for improvement. At 6.1 millibars, it is only a thin remainder. So the scale has reversed. Mars does not begin halfway toward an Earth-like greenhouse, with enough pressure already present and only warmth missing. It begins at about 0.6% of Earth's sea level pressure. More than 99% of the atmospheric burden needed merely to match Earth's pressure is absent. Carbon dioxide seems like the easiest place to look because Mars already has it in the air, frost, soil, and rock. Release more gas, and it should trap more heat. A warmer surface could then freeze still more carbon dioxide, raising pressure and temperature together. It sounds like opening the planet's storage tanks and letting their contents build a new sky. The trouble is that those tanks are much smaller than they appear. In 2018, planetary scientists Bruce Jakosky and Christopher Edwards counted the carbon dioxide that modern Mars might release. They included the polar caps, carbon attached to shallow soil, and minerals near the surface. Their estimate was generous about material, that future technology might recover, even when extraction would be difficult. The polar deposits are the most tempting target. Mars visibly trades carbon dioxide between its atmosphere and polar frost as the seasons change. Radar observations have also revealed buried deposits beneath the south polar cap. Directing extra heat toward the ice could release those stores and thicken the air. Even if all accessible polar carbon dioxide escaped, though, Mars would remain far short of the heavy atmosphere needed for broad, lasting warming. The soil holds some as well. Carbon dioxide clings to tiny grains, but much of the ground would have to be heated before the gas came free. Doing that across Mars would take immense amounts of energy, and the return would still be limited. The soil could add pressure, but it couldn't supply the missing mass. Carbon-bearing minerals may sound more promising because rock can preserve carbon for a very long time. NASA's Mars Reconnaissance Orbiter mapped carbonate deposits from orbit, while the Spirit and Curiosity rovers examined rocks below. The minerals exist. Spacecraft simply haven't found them near the surface in the vast, reachable quantities this plan requires. Heating or crushing scattered deposits doesn't solve the shortage when there is too little accessible rock to start with. Some carbon may lie much deeper beyond current measurements. No one can rule that out. Yet hidden carbon isn't the same as a usable reserve. Finding it, mining through kilometers of crust, and releasing it across Mars would require deposits for which we don't yet have evidence. An unseen supply can't be counted just because the measured total falls short. Even with optimistic assumptions, releasing the known accessible stores adds only a small share of the pressure needed for stable planetary warming. Mars might gain a somewhat thicker atmosphere, and a few places could briefly become warmer. It would still be a cold, low-pressure world. That is enough to change Mars, but nowhere near enough to remake it. The polar caps contribute some gas. The shallow soil contributes less. The mapped carbonate rock doesn't close the gap. Empty every known tank, and the thick carbon dioxide blanket becomes only a thin extra layer. That thin extra layer wouldn't be worthless. Carbon dioxide traps heat, so adding some to the Martian air could raise temperatures in certain places and seasons. Inside sealed habitats, it could also help warm greenhouses, where sunlight enters through clear panels and heat escapes more slowly. Those are real benefits, even if they fall far short of warming the whole planet. The settlers could also use carbon dioxide as a raw material. Mars has plenty of it in the air, even though the atmosphere itself is very thin. Machines could collect the gas and feed it into chemical systems that make oxygen, fuel, or carbon-based materials. Plants grown under glass would use it as well, drawing in carbon dioxide while light provides the energy for growth. In that setting, the gas becomes something people manage, store, and put to work. This is a smaller role than turning Mars into a second Earth, but it may be far more practical. A settlement doesn't need to change an entire planet before it can improve the conditions inside a greenhouse or produce fuel for a vehicle. It can work with a limited supply, recycle what it uses, and keep the process within walls that engineers can monitor. Carbon dioxide may be valuable precisely because no one has to spread enough of it across the whole Martian surface. Still, a useful greenhouse gas isn't the same as useful air. You could fill a greenhouse with extra carbon dioxide for the plants, while keeping the people who tend them behind masks, partitions, or sealed work areas. Human lungs need oxygen, and the surrounding gas must provide enough total pressure for the body to function safely. Carbon dioxide can contribute to that pressure, but increasing its share creates another problem. At concentrations far below the level needed for a thick Martian atmosphere, it becomes dangerous to breathe. So the gas can help in controlled places without becoming the main substance around every person. It can warm a growing room, supply a chemical plant, or become part of a fuel-making cycle. None of those jobs requires anyone to breathe it. We can use the same gas as a resource in one room and treat it as a hazard in the next. The distinction sounds almost awkwardly simple, yet it separates two goals that are easy to blur together: using what Mars provides and making the open air fit for human life. A planet-wide atmosphere must do more than hold in warmth. It must press against the body at a safe level, carry breathable oxygen without making fires unmanageable, and avoid poisoning the people standing in it. Carbon dioxide can support pieces of that system, but it can't stand in for the whole system. If most of the air shouldn't be oxygen or carbon dioxide, then what gas could provide the missing pressure? Breathable air is not just oxygen floating near your face. It is a physical load pressing against every part of you, including the wet surfaces inside your lungs. Without enough total pressure, oxygen molecules may be present and still fail to enter the blood in a useful amount. The gas may be right while the environment remains deadly. Mars has an atmosphere, but the pressure at its surface averages less than 1% of the pressure at sea level on Earth. Standing outside would be much closer to entering a vacuum chamber than climbing a high mountain. Adding a little oxygen would not fix that. Your lungs need enough oxygen pressure to move oxygen into the blood, while your body needs enough surrounding pressure to keep its fluids stable. A pressure suit solves both problems locally. It holds gas around the body, giving the lungs something substantial to breathe and preventing the near vacuum outside from acting directly on exposed tissue. That is why carrying an oxygen tank would never be enough on Mars. You need the tank, the sealed suit, and the pressure inside it. Remove the pressure, and breathable molecules alone cannot make the surface safe. It might seem possible to raise the oxygen share until every breath supplied enough. Yet this creates another danger. Oxygen helps many materials catch fire and burn faster, so a small spark can become a severe emergency. NASA learned this through spacecraft design, where cabin pressure and oxygen concentration must be managed together. Across a settled planet, oxygen-rich air would make clothing, plastics, plants, and buildings far harder to protect from fire. Earth avoids that danger by using nitrogen as most of its atmosphere. Nitrogen does not feed our cells as oxygen does, but it supplies much of the pressure around us and dilutes oxygen to a safer concentration. Argon and several other gases add a little more. We breathe because oxygen is included, but we can walk outside because the whole mixture works together. That changes the scale of terraforming Mars. Producing oxygen from carbon dioxide or water could fill one part of the atmosphere, but it would not create open air that people could safely enter. Mars would still need an immense supply of another gas, one that adds bulk without poisoning people, reacting with nearby materials, or making fires much easier to start. Mars does not have an obvious reserve of that gas waiting at the surface. Nitrogen exists there only in small amounts, while argon is present but falls far short of an Earth-like atmospheric blanket. The missing ingredient is therefore more than something breathable. It is the huge background mass of air that lets oxygen do its job without becoming a hazard. Finding enough of that background gas is the next difficulty. Mars can make nitrogen look less scarce than it is, because the number most often quoted is a percentage. Nitrogen makes up about 2.7% of the Martian atmosphere. That sounds like a small but usable share, yet a percentage tells us only how the gas is divided within the air that exists. It says nothing by itself about how much air is pressing down in the first place. At the Martian surface, the total air pressure averages less than 1% of Earth's sea level pressure, though it changes with elevation, weather, and season. Multiply that low pressure by nitrogen's 2.7% share, and the result is a nitrogen partial pressure of only around 16 pascals. On Earth, nitrogen alone presses down with roughly 78,000 pascals at sea level. The Martian value is less than 1 part in 4,000 of that. So a cubic meter of Martian air contains only a tiny fraction of the nitrogen found in the same volume around you now. Partial pressure is simply each gas's contribution to the total pressure. If several people were holding up a heavy table, the percentage would tell you what share of the work belonged to one person. It wouldn't tell you whether the table weighed 10 pounds or 1,000. Mars has given nitrogen a visible share of an extremely light table. This distinction changes the scale of the problem. Suppose engineers could separate every nitrogen molecule from a large amount of Martian air. They would begin with so little gas that building a thick atmosphere would require processing an enormous volume. Even collecting all of it would only gather what was already present, spread thinly across the planet. As nitrogen was removed, the remaining atmosphere wouldn't somehow replace it. the total supply is limited by the small mass of air surrounding Mars. Measurements by Viking, Curiosity and other Mars missions have refined the mix of gases near the surface, but none has revealed a hidden atmospheric reservoir large enough to solve this. There may be nitrogen locked in minerals or buried deposits that haven't been fully measured. Scientists can't yet give a final inventory. Still, no known source offers anything close to the amount required for a planet-wide blanket resembling Earth's. That is why 2.7% can mislead the ear. It sounds as though Mars already has some of the needed ingredient, when the physical amount is thousands of times too small for the role nitrogen plays here. If the planet can't supply the background gas from its present air, then it must come from somewhere harder to reach, be replaced by another suitable gas, or be brought in from beyond Mars. Each choice turns a missing atmosphere into the task of moving almost unimaginable mass. Mars can lose atmosphere in several ways, and billions of years give even a slow loss time to add up. High above the surface, sunlight can break gas molecules into charged pieces. Collisions can also give individual particles enough speed to escape, while the solar wind can carry some of them away. Any plan for a lasting atmosphere has to account for those leaks. Still, stopping a leak and filling an empty tank are separate jobs. You can see why the two jobs are so easy to confuse. Keeping gas sounds like a step toward having more of it. If engineers could slow the escape, each molecule released from Martian rock or delivered from elsewhere would stay longer. Less replacement gas might be needed as the centuries passed, perhaps much less. That could make an atmosphere easier to maintain after it began forming. It wouldn't create the immense first supply needed to build one. Mars wouldn't become airtight after one intervention either. Gases escape at different rates, and those rates change with altitude, temperature, sunlight, and the chemistry of the upper atmosphere. A system that blocks one path might leave another untouched. Even a highly effective barrier would need to work for centuries, while dust storms, equipment failures, and changing solar activity pressed against it. Retention would be a continuing task over many human lifetimes, carried by machines that need repairs, and by people who cannot treat the atmosphere as finished. The order matters because there must be something to retain. Gas would first have to be released from Martian material, manufactured from available elements, brought from somewhere else in the solar system, or supplied through a combination of those routes. Whichever route is chosen, enough mass must enter the air to raise pressure across an entire planet. Slowing later losses may lower the amount needed for replacement, but it doesn't erase the amount needed at the start. A successful retention system could therefore be remarkable and still leave Mars nearly airless. It might protect every new shipment and let pressure rise instead of fading as quickly. Yet, if those shipments are tiny beside the required total, the protected atmosphere remains tiny as well. A lid can preserve what has been placed beneath it. It cannot provide the contents. That distinction is easy to miss in ambitious proposals. A shield might answer how to keep a built atmosphere from thinning too quickly without answering where its gas comes from. An escape control system might improve the final balance while doing almost nothing for the first delivery. Supply decides whether Mars can gain a substantial atmosphere. Retention decides how long that atmosphere can survive. Both need answers, but they are not interchangeable. Can any shield, barrier, or escape control system make a practical difference before enough gas has been found to assemble the atmosphere it is meant to protect? The strongest magnetic shield proposal begins far from the Martian surface, near a place called Mars L1. That's a point in space where the pull of Mars and the Sun allows a spacecraft to stay in roughly the same position relative to the planet. From there, a large magnetic field could stand between Mars and the solar wind. The solar wind is a stream of charged particles flowing outward from the Sun. Mars meets that stream without the broad global magnetic field that protects Earth. When those particles interact with the upper atmosphere, they can help knock atmospheric particles into space. A shield placed upstream could push part of that flow around Mars before it reaches the air. This isn't just a force field borrowed from science fiction. Charged particles really do change course in magnetic fields, and spacecraft already use balance points between planets and the Sun. In 2017, NASA scientist Jim Green and his colleagues described a magnetic dipole placed near Mars L1. Their computer models suggested it could reduce solar wind stripping and allow the atmosphere to build over time. The key words are over time. A shield wouldn't make air appear at the surface, and it wouldn't turn today's thin carbon dioxide into a breathable sky. Its job would be narrower. Once people had released, imported, or manufactured a much larger atmosphere, the shield might slow one route by which that work could be lost. Even then, several parts remain uncertain. The field would need to divert the solar wind across a planet-sized region, while the hardware producing it would sit in space and require power, cooling, control, and repair. Researchers can model the magnetic bubble, but nobody has built anything close to this scale. We also don't know exactly how the upper atmosphere would settle after shielding, because sunlight and chemistry would keep driving other forms of escape. Blocking one loss process wouldn't block them all. Still, the proposal deserves serious attention because it addresses a measured process. NASA's MAVEN spacecraft has watched the solar wind remove particles from Mars, with loss increasing during solar storms. A magnetic shield aims directly at that interaction. It could give a costly artificial atmosphere a longer working life, especially across centuries, when even slow leakage adds up. That wouldn't solve every problem, but it could protect years of work already done. That places the shield late in the sequence. First comes enough gas, then enough pressure, followed by a way to limit future loss. If Mars ever reaches that point, keeping the new atmosphere may become one of the largest engineering jobs around the planet. Before anyone can protect that air, though, how could people produce enough of it to change conditions on the ground? A magnetic shield can slow the escape of an atmosphere, but slowing a loss is not the same as creating what was never there. It is like closing a drain after finding the bathtub empty. The plug may work perfectly. You still need water from somewhere else, and on Mars, every part of that refill would have to be found, processed, moved, or made. Retention changes the pace of the problem. If a new gas supply took decades to build, better retention could keep more of each year's production in the sky. That would reduce how often the system had to replace escaped molecules, and it could lower the burden placed on future factories. Yet the shield itself would contribute no carbon dioxide and no nitrogen. It would not raise the pressure by a single breath until another system supplied the gas. The same limit appears once people begin asking what the atmosphere is for. Pressure and warmth could make surface work less punishing, but crops do not live on pressure alone. Farms need water delivered in a controlled cycle, nutrients returned to the soil or growing beds, light, power, and protection when any part fails. A shield supplies none of those things. It preserves an input. It does not build the system that turns that input into food. Nor would retained air become roads, power stations, storage tanks, repair shops, or homes. Those would still require materials, machines, skilled labor, and years of steady maintenance. Even a successful planetary shield would sit above that work like a roof over an unfinished building. The roof can prevent more damage, but it cannot install the plumbing underneath it. This also changes what success would look like. The atmosphere might stop thinning so quickly, while life on the ground remains dependent on sealed rooms, managed water, imported equipment, and constant repair. From orbit, the air could seem more secure. For the people below, the settlement would still need nearly everything. This distinction changes the scale of the plan. A leaky Mars forces settlers to manufacture replacement gas while they are also trying to expand everything else. A better retaining Mars eases that repeated cost, perhaps by a great deal, yet the first supply must still be produced, and the life-supporting systems must still be assembled. Retention can protect an investment. It cannot make the investment on its own. So the next step is not another way to hold the atmosphere in place. It is a source, enough carbon dioxide, nitrogen, and working water to feed a living settlement, followed by the farms and machines that keep those materials moving instead of letting them become a dead stockpile. If Mars does not already offer enough accessible gas, what process could people use to manufacture it? Any atmosphere people manufacture would still be precious. A shield could slow its loss and protect that investment once a settlement had enough gas worth protecting. That gives the shield a real place in the plan, only later. It would be a stabilizer, not the starting supply, and it couldn't replace the mines, power plants, chemical systems, and years of work needed to build that supply. Mars does offer one inheritance in meaningful quantity: water. Spacecraft observations and surface missions have found it in polar ice, buried deposits, hydrated minerals, and traces within the soil. How much settlers could reach would depend on where they landed and what equipment they brought. But the broad finding is secure. Mars isn't dry in the simple sense. Much of its water is frozen, buried, or bound inside rock. That is a different advantage from an atmosphere, but for the first cruise, it may be the more immediate one. For a settlement, that difference is enormous. Water can be drunk, used for washing, passed through farms, and split into hydrogen and oxygen. The oxygen can support breathing, while hydrogen and oxygen can also become rocket propellant. One local material could serve daily survival, food production, industry, and transport. It doesn't have to surround a whole planet either. People can gather it and keep it inside a much smaller controlled system. Still, finding ice isn't the same as opening a tap. Settlers would have to reach it, remove soil, or drill through rock, melt the ice, clean the water, and stop it from freezing again. Every link in that chain needs equipment and power. At the low pressure on the Martian surface, exposed liquid water is unstable, so most usable water would remain inside pipes, tanks, greenhouses, and pressurized rooms. If you stepped outside, you wouldn't find streams waiting for a bucket. Water is therefore more promising than the missing atmospheric gases. Though it isn't effortless, it appears to exist in amounts large enough to affect where settlements could grow. People wouldn't need to import every glass from Earth or manufacture each molecule from scratch. They would inherit a local stock, then pay the continuing energy cost of turning it into flowing water and keeping nearly all of it in circulation. The shield belongs after that work has begun. If Mars ever carries a thicker manufactured atmosphere, slowing its escape could make each new ton last longer and reduce the burden on later generations. Yet the first settlements would live or fail through smaller loops, with water recovered, cleaned, used, captured, and used again under pressure. Mars has the raw material. How could we turn frozen and buried water into a dependable supply without spending more energy than a settlement can spare? Mars holds a great deal of water, but that fact can be misleading. Most of it is locked in polar ice, mixed through frozen ground, bound inside minerals, or buried where no early settlement could reach it cheaply. A planet can be rich in water while the people living on it still count every liter. The difference is access. Ice sitting near the surface may look like a ready supply, yet miners would still have to uncover it, break it apart, move it into sealed equipment, melt it, and remove whatever came along with it. If the ice lies deeper, every meter of digging adds machinery, heat, maintenance, and time. Water inside rock is harder still, because freeing it can require crushing and heating large amounts of material for a much smaller return. Location also changes the answer. Some of the best water deposits may lie far from safe landing sites, steady sunlight, or places suited to building homes. A settlement beside abundant ice could face poor power conditions. Another built where solar panels work well might have to haul water across difficult ground. Mars does not place every resource together for our convenience, and total volume says little about the rate at which water can be produced. A buried deposit might contain enough ice for centuries, while the equipment above it can supply only a few families each day. Pumps and drills wear down or jam, while seals leak and dust enters moving parts. During a failure, the water beneath the ground is still there, but it is no more helpful than a lake behind a wall with no working pipe. That is why reachable water is partly an energy reserve. Each litre has an energy price before anyone drinks it. It must be extracted, warmed, cleaned, moved, and stored without freezing again. The settlement then has to recover water from breath, washing, food preparation, and waste, because replacing every loss from the ground would keep that price painfully high. That gap would shape daily life from the start. Over time, larger reactors and better mining systems could make some deposits far easier to use. Settlers might also choose new towns around shallow ice, instead of forcing every town to depend on long supply lines. Even then, estimates made from orbit cannot tell us exactly how clean a deposit is, how firmly it is mixed with soil, or how extraction machinery will behave there for decades. Those answers require drilling and long tests on Mars itself. So the first descendants may live on a world with enough water to cover every human need many times over, yet have only a narrow daily supply passing through their tanks. Their survival would depend less on how much water Mars owns than on how fast they can reach it, process it, and recover it after use. If usable water remains this costly, how would it shape where Martian communities can grow? In practice, you can think of a map of Martian water as a rough map of where people could afford to live. A broad patch of buried ice may look promising from orbit, but a settlement cannot use color on a map. It needs a deposit close enough to the surface for machines to reach, thick enough to repay the digging, and near ground where a town can safely be built. Depth changes almost everything. Ice lying just beneath loose soil might be uncovered with manageable equipment. If the same ice sits under several meters of frozen ground and rock, crews must move far more material before collecting a single load. The machinery grows heavier, demands more power, and wears down faster. A deeper deposit may contain more water and still be the worst choice. Latitude adds another constraint. Mars tends to preserve shallow ground ice better in colder regions away from the equator. Those regions may offer easier access to water, yet they also bring longer winters, weaker sunlight, and lower temperatures. Solar panels produce less energy when the sun stays low, while heaters must work harder to protect people, pipes, batteries, and moving parts. A site can save energy on digging and spend that saving on staying warm. Closer to the equator, sunlight is generally more favorable and temperatures are less severe, but accessible ice may be scarcer or buried farther down. Early planners would therefore be choosing between different kinds of expense, with no location winning every comparison. The best place for water may not be the best place for power, landing, travel, or long-term construction. Transport makes these differences spread across the planet. Water is heavy, and moving it over rough ground costs energy at every kilometer. A distant mine would need vehicles, charging points, spare parts, protected storage, and a route that remains usable through dust and cold. Sending water from one region to another could cost so much that a second settlement near its own deposit becomes cheaper than extending the first town across dry ground. That gives buried ice a political weight as well as a practical one. Communities founded beside dependable deposits could grow sooner and support workshops, farms, and visiting crews with less imported mass. Places without local water might remain small outposts, even if they offer better science or smoother landing terrain. Roads and power lines would likely follow the same corridors, joining sites where water can be reached without consuming most of the energy it provides. These patterns would not be fixed forever. Better drilling, nuclear power, or cheaper transport could open ground that first settlers had to avoid. Yet the earliest choices would leave marks: buildings, landing pads, repair shops, and families gathered around the deposits that were easiest to reach. Once that investment exists, moving becomes harder. If water chooses the first Martian towns, who gets to control the ground beneath them? Controlling a patch of ice would not mean controlling a ready-made town. It would mean controlling a difficult work site, where every useful drop still has to be dug out, cleaned, moved, and kept from escaping. A settlement might sit above a rich deposit and still need months of careful processing before anyone could drink from it. Some Martian ice may be mixed through soil or buried beneath layers that shield it from sunlight. Crews would need drills, heaters, pipes, filters, and enough power to keep them running through cold nights and dust storms. Heating the ground could release water vapor, which machines would capture and condense. Other deposits might be cut out and carried into sealed processing rooms. In either case, the ice becomes usable only after a long chain of machines has done its work. Then that water has to become part of the settlement. Some might be split to help make oxygen and fuel. Some would pass through kitchens, showers, medical rooms and growing areas. Most could not be used once and discarded. It would need to circle back through filters, tanks and treatment systems, because replacing a lost supply might require another drilling shift, another heavy draw on the power system, and more equipment that can break. Storage would be almost as important as extraction. A broken pump should not leave a habitat dry by morning, so separate tanks would need to hold enough reserves for repairs. Pipes would need protection from freezing, and crews would need ways to isolate a leak without shutting down the whole settlement. On Earth, a dripping pipe is often a repair bill. On Mars, the same leak could threaten drinking water, air production, hygiene, food growing, and the fuel set aside for vehicles. Reliability would become daily engineering rather than a feature added later. While backup equipment carried the load, crews would inspect seals and tank levels before cleaning filters and practicing repairs. In this way, maintenance would support the settlement as directly as extraction. You could stand directly above all the ice a settlement might need and still be unable to live there without pressure. The sky remains thin, the air outside cannot support a human body, and exposed liquid water would not sit calmly in a pond as it does on Earth. People would spend their days inside sealed rooms, moving through protected passages or putting on suits whenever they crossed open ground. Local ice might reduce deliveries from Earth, but it would not remove the walls between people and Mars. The first water-rich settlement would probably feel less like an open town and more like a mining and processing camp, learning, piece by piece, how to become a home. Its most important spaces may be the ones a visitor barely notices: pump rooms, reserve tanks, recycling units, repair benches, spare filters, and warm sleeping areas kept safe by machinery nearby. If water still has to be turned into pressure, storage, recycling, and dependable indoor life beneath that thin sky, what do people actually build first? The first people born on Mars may inherit a world made mostly of walls. Their parents would have built shelters against radiation and workshops that hold breathable air, all supported by power systems that can't be left unattended for long. Growing up there would mean learning why someone checks seals, clears filters, and repairs cables before anything fails, so that work would shape the first generations. They wouldn't begin by planting forests beneath a blue sky. They would quarry rock, bury living spaces, and expand protected tunnels from one pressurized room to another. Mars offers plenty of material, but turning it into shielding takes machines, energy, and time. Every new room adds more air to manage, more joints that can leak, and more equipment that future crews must understand. Terraforming at this stage would look less like changing a planet and more like spreading life support. One greenhouse becomes larger, and then another greenhouse joins it. A water plant serves more homes. Waste heat warms a neighboring room instead of escaping. Carbon dioxide from people and machines feeds plants or chemical processing. The settlement grows by linking systems that once worked alone, until a failure in one place can affect families living far away. You can see the human difficulty inside that progress. A machine might last 20 years, while the settlement must last for centuries. The people replacing it may never meet its designer. Instructions must last even as language changes and parts wear out. Repairs may slowly reshape a machine until it differs from the design sent from Earth. People would learn maintenance as carefully as medicine, because both keep them alive when help is months away. Children would practice repairs as well as read manuals. Radiation shielding brings the same long view. Mars has little atmosphere and no global magnetic field like Earth's, so the surface offers weak protection from charged particles arriving from space. Thick layers of soil or rock could lower that exposure inside homes, but covering one habitat is different from protecting an expanding community. Each school, clinic, farm, and factory needs its own safe volume or a protected route leading to one. Over many lifetimes, those covered spaces could begin to join. Pressurized districts might spread beneath soil and through lava tubes, with other structures assembled from local material. Children could then travel between the places that shape daily life without crossing the exposed surface each day. To someone outside, the cold desert might look unchanged even after generations had extended shelter far enough for air and warmth to persist across connected districts. Once that network became dependable, settlers could spend more effort changing conditions beyond the walls. So how could these enclosed islands of life ever begin to alter the air of an entire planet? Rather than a small Earth town placed under a glass roof, a Martian city would be a machine large enough to contain public life in all its daily confusion. Walls would hold the pressure, as shielding softened radiation and hidden pipes carried water and waste. Inside, someone could miss a bus or hurry home in air that existed only because the city kept making it. That normal life would be a major achievement because people cannot spend every hour watching gauges like a spacecraft crew. They must be able to live private lives, disagree in public, and sometimes forget a maintenance schedule without turning each loose seal into a crisis. Children born there would know Mars as home rather than a mission, so life support might become something learned in school but rarely considered during lunch. Yet an enclosed Martian city could never let people forget the machinery behind daily life. On Earth, a broken heating system can make a building dangerous. On Mars, failures in heating, pressure, air recycling or water recovery could spread across a whole district. That would make maintenance part of government. Budgets, inspections, spare parts, training, and repair access would shape public safety as directly as hospitals and fire departments do now. Engineers would design layers of protection so one failed pump or damaged wall did not empty a neighborhood. Sealed sections and smaller air loops could keep one fault from spreading, with reserves distributed instead of gathered at a single weak point. Failure would remain possible, but people would gain time to respond, and could often turn a potential disaster into an inconvenience. The social effects could be surprisingly familiar, with residents arguing over which district gets a new pressure tunnel first. Other debates would concern an aging farm chamber, or the tax needed for equipment no one notices when it works. Technicians might become trusted public figures, or unpopular ones when repairs close a busy route. A city council meeting about valve standards sounds almost comically dull until you remember that everyone at the meeting is breathing through the result. So the first Martian cities would be extraordinary on the outside and deeply human within. Their cafes, clinics, playgrounds and crowded homes could feel settled, while meters of shielding and a web of machines kept that feeling possible. Yet even a well-run enclosed city would still consume power, replace worn equipment, and depend on skills passed from one generation to the next. If those cities grew across Mars, where would they get enough energy to keep all that air warm and moving? A Martian city would probably draw power from several sources. None works perfectly through every season or emergency. Solar panels turn daylight into electricity, though dust and storms can weaken them. Nuclear reactors provide steady power through darkness and bad weather, but they need trained care and working support equipment. The city may need both sources, plus enough stored energy to survive trouble in either system. That power does much more than keep the lights on. It keeps air moving, water clean, rooms warm, and workshops able to make replacement parts. Some energy could remain in batteries while another share became chemical fuel, but storage has limits. Since a long failure would gradually take away livable conditions, spare capacity would be part of daily survival, rather than a reserve saved only for rare emergencies. That limit changes what growth would mean on Mars, where the first prize would not be walking outside without a suit. Open Martian air may remain dangerous for a very long time, perhaps forever. Growth would mean adding a district without making the older one less secure. New homes would still need enough spare power for a bitter night, while systems would have to fail in small pieces instead of bringing down the whole city. Children born there would inherit those systems before they inherited much scenery. Their home might include windows looking across rust-colored ground, but their daily world would be shaped by airlocks, pressure doors, water rules, and the soft sound of fans behind the walls. If you were born there, those fans might feel as natural as rain sounds on Earth. Mars would be home because people had learnt to keep making a safe place inside it. That includes the farms. Plants need several conditions at once, all managed by the settlement. Water would return through a cleaning loop, and bring measured nutrients to crops receiving carbon dioxide. During short winter days, lamps would help crops grow. Greenhouse walls would hold pressure and block harmful radiation, while processed waste returned usable elements to the roots. A mature settlement might serve a varied meal grown only a short walk away, and that could feel like proof that the city had finally settled in. Yet the field would remain a sealed room with seasons set by machinery. Each harvest would rely on measured nutrients and equipment that people carefully maintain. So why would even food, the clearest sign of a lasting settlement, still begin inside engineered chemistry? Martian soil is not waiting for someone to scatter seeds across it. The loose material covering the surface is regolith, broken rock, sharp dust, and salts changed by radiation and dry chemistry over immense spans of time. It may contain minerals plants need, but that does not make it ready to feed them. Before it enters a greenhouse, it has to be treated as possible contamination. You would have to prove each batch safe first. One concern is perchlorate, a family of chlorine and oxygen salts detected on Mars. NASA's Phoenix lander found perchlorate in northern soil in 2008, and the Curiosity rover later found evidence of related chlorine compounds inside Gale crater. The amounts vary by place, and scientists still do not have a complete map. Even so, the warning is clear. Some Martian material contains chemicals that can interfere with human thyroid function and enter crops if they are not removed or controlled. The dust brings another problem. Martian grains have not been softened by flowing rivers, busy ecosystems, or generations of plant roots. They can be fine, abrasive, and easy to carry into machinery or living spaces. Once inside a pressurized farm, that dust could settle on equipment, cling to clothing, and become something people breathe. A farmer could not simply open a door and bring in a load from outside. Then there is what the regolith lacks. Earth soil is alive with bacteria, fungi, decaying matter, air pockets, and carbon compounds built up by earlier life. Martian regolith has no known living soil community and very little of the material that makes a garden bed fertile. Its texture may also hold water poorly or pack around roots. Adding fertilizer alone would not recreate the working system beneath an earth garden. Researchers have grown plants in volcanic material made to resemble some Martian minerals, but those experiments use substitutes, not soil returned from Mars. They show that mineral grains can support growth after water and nutrients are added, without proving that untreated Martian regolith is safe for crops or people. Before using regolith, a settlement might wash away soluble salts and separate the finest dust, then test each batch before mixing the cleaned minerals with compost made inside the city. Heat or biological treatment could also help, though either method would demand water, equipment, and careful checks. Early farms may avoid local regolith altogether and keep roots in water or prepared material from earth. That makes the first farming task less like planting and more like handling a suspect industrial powder. Mars may provide part of the physical base, but the city must decide what can safely enter its food cycle. If the ground itself needs cleaning before it can touch a root, what would a dependable Martian farm actually grow in? A dependable Martian farm would begin with prepared growing media, not a shovel pushed into the ground. After local minerals were washed and tested, settlers could blend them with safer material made inside the city. The result might look like soil, yet its water flow and chemistry would be known because every handful carried a production record. Roots need more than something to hold them upright, because the material around them must carry water without shutting out air. If packed too tightly, roots can suffocate. If left too loose, water can drain away too quickly. Earth soil gains structure through living activity and weather over long periods. A Mars farm would build its version deliberately and keep checking how each crop changed it. Some farms would skip soil-like media and place roots directly in moving water. Hydroponic systems can deliver nutrients in measured amounts, while aeroponic systems mist exposed roots. Both reduce dependence on regolith, though neither removes the need for close control. A clogged pipe, a failed pump, or the wrong nutrient balance can affect many plants at once, because they share the same loop. That shared water cannot simply disappear after passing the roots. Moisture released by leaves would condense on cool surfaces before cleaning sent it around again, and drainage would return to the same guarded cycle. Sensors could watch the water chemistry, while treatment units removed anything the plants should not receive on the next pass. Waste would enter through a separate guarded route. Crop stems, food scraps, and human waste all contain nutrients the farm will need, especially nitrogen and phosphorus. Yet they can also carry pathogens, medicines, cleaning chemicals, or concentrations of salt. Composting, heat treatment, and chemical processing may recover much of that value, but the recovered material would still need testing before it reached edible crops. This is where contamination control becomes part of farming. A fungus in one tray, a toxic batch of processed minerals, or a microbe surviving waste treatment could move through shared water and reach several growing rooms. Early settlements would likely divide crops into smaller loops, quarantine new batches, and keep seed reserves away from active production. The separation costs more equipment, but it prevents one failure from becoming everyone's dinner problem. Only after those linked systems work together does the room begin to feel like a greenhouse, with green leaves under lamps and food growing within reach through damp air. Until then, the vegetables occupy a clean room supported by water treatment, recycling, and laboratory work. Once that controlled farm is running, which crops should receive its limited space first? The first crops would earn their place by doing several jobs at once. A settlement needs calories, but it also needs food that grows reliably inside a closed room, uses little space, and becomes meals people will accept after years away from Earth. A plant that performs well in a field may be a poor tenant under lamps. Fast-growing greens can offer fresh flavor and vitamins, yet they don't provide enough energy to carry a city. Staple crops could supply far more of the daily diet, though wheat, potatoes, and soybeans would each place different demands on the farm from planting through storage. Choosing crops becomes less like planning a garden and more like fitting a small food economy into a building. Then there's appetite. We don't eat nutrients as numbers on a screen. Texture, smell, familiar recipes, and the chance to share a meal can affect how much food gets eaten, wasted, or traded. A menu designed only for efficiency might wear people down over time. A Mars kitchen has to feed bodies without making every dinner feel like medical treatment. As farms improve, the selection could widen. Carefully pruned fruit trees and compact herbs could bring new tastes without using much room. Fungi might turn plant material into food, and other enclosed sources of protein could add further choices. Each addition, however, would introduce another living process that might become sick or demand scarce resources during an emergency. Even a successful farm remains part of the sealed city. Its lamps need power, its roots depend on prepared water and measured nutrients, and its air passes through machinery. The harvest reaches people through rooms built to keep Mars outside. Farming can reduce shipments from Earth and make life much safer, but it doesn't spread across the planet. It extends the indoor world. You could stand among rows of green leaves and feel that Mars was becoming Earth-like. Yet enclosure and constant care would still keep those leaves alive. If the walls failed, the planet would not take over the work. Cold and thin air would reach the crops, and their living world would end at the broken structure. Food production could show that people had learned to maintain a larger shelter, one capable of supporting fuller homes and more varied meals. Life inside might become safer and richer as a result. Still, a comfortable settlement could approach self-sufficiency without changing Mars beyond its walls. Oxygen may be a harder test, because producing it at great scale could support breathing and fuel, as well as metalworking and, perhaps much later, places beyond a habitat. If Mars cities learn to handle vast amounts of oxygen from production through storage and delivery, does that finally prove the larger industrial transformation is underway? MOXIE arrived on Mars inside NASA's Perseverance rover in February of 2021. About the size of a car battery, it sat beneath the rover's deck with one job: take the thin Martian atmosphere and make oxygen from it. The oxygen wasn't carried from Earth. The machine had to make it there, using the carbon dioxide surrounding the rover. That April, engineers at NASA's Jet Propulsion Laboratory switched MOXIE on for the first time. It drew Martian air through a filter, compressed it, heated it, and passed it through a solid oxide electrolysis system. Inside, carbon dioxide molecules split apart, carbon monoxide left as waste, while oxygen atoms joined in pairs to form the same gas people breathe and rocket engines use. The device had to reach nearly 1,470 degrees Fahrenheit, about 800 degrees Celsius, before the process worked. The first run produced only a few grams. Across 16 runs, MOXIE made 122 grams of oxygen, roughly enough to keep a small dog breathing for 10 hours. Set that beside the needs of one person, much less a city, and it seems almost comically small. Yet MOXIE wasn't built to supply anyone's air. It was built to prove that the full chain could work on Mars, through changing seasons and at different times of day, with the actual atmosphere instead of a gas mixture prepared in a laboratory on Earth. And it worked. During its strongest run, MOXIE produced about 12 grams of oxygen in an hour, and its output reached high purity. You could point to a machine sitting on another planet and trace the result from beginning to end. Martian air entered, the carbon dioxide was processed, and usable oxygen came out. That turned a sound chemical proposal into a physical achievement on Mars. A future oxygen plant would have to be vastly larger. It would need dependable power, dust control, replacement parts, storage tanks, pipes, compressors, and people or robots able to keep it running for years. Making enough oxygen for breathing would already be demanding. Making the much greater amount needed to burn fuel for a crewed launch would make the plant major infrastructure, tied directly to whether people could leave Mars safely. MOXIE didn't show that such a plant would be cheap, durable, or easy to repair. It didn't show that settlers could expand one quickly when equipment failed or demand rose. What it showed was narrower but firm. The central conversion can happen in the place where it must happen. So there is still a wide gap between a successful box beneath a rover and an industry people can trust with their air and their route home. If Mars can supply oxygen, what else must its settlers learn to build before that small chemical success can support a lasting human world? MOXIE was a prototype, and prototypes are allowed to live sheltered lives. It received electricity from the rover, ran for limited periods, and sent its results back to engineers on Earth. If a seal wore down or a filter began to clog, nobody nearby was depending on that machine for the next breath. A city would give the same chemistry a much heavier job. Its oxygen plant would need to draw in dusty Martian air every day, compress it, remove material that could damage the equipment, and keep carbon dioxide moving through the reactor. The oxygen coming out would then need to be checked, cooled, moved, and stored without leaking away. Each part adds another way for the system to stop. Mars dust can settle inside moving equipment. Seals can become brittle, pumps can wear out, and sensors can drift until they report a reassuring number that is no longer true. We might not notice the fault until production has already fallen. Even a small failure becomes serious when the plant serves homes, clinics, farms, workshops, and spacecraft tanks. Settlers would need more than a working reactor. They would need spare parts, repair tools, trained crews, and enough stored oxygen to cover shutdowns. They would also need backup production lines, since maintenance cannot wait for everyone to stop breathing. A machine that works most of the time may perform well during a test. For a settlement, most of the time isn't enough. Then there is growth. A plant sized for a few dozen people cannot simply be asked to supply a growing town. More residents mean more breathing air, while larger farms and metalworking raise demand as well. Making fuel for spacecraft would add a far greater draw, perhaps in bursts before a launch. The system must cover daily use while still filling reserves for emergencies and future missions. This is the difference between proving a reaction and building infrastructure. The reactor sits at the center, but it depends on electrical power, intake equipment, storage tanks, pipes, control systems, maintenance shops, and people who know how the pieces work together. If one vital component can only be replaced by a shipment from Earth, the settlement has gained a machine without gaining full control over it. A lasting city would slowly have to make more of those components on Mars. It might begin with simple filters and fittings, then move toward pressure vessels, motors, electronics, and the specialized materials inside the reactor. Every part made locally removes a delay measured in months and one more launch that has to arrive safely. MOXIE showed that a reactor can pull oxygen from Martian carbon dioxide. The harder task is keeping the whole chain running while people sleep, work, get sick, repair other machines, and face failures they cannot schedule. So which industries must stand beside the oxygen plant before a settlement can truly maintain itself? The industries beside an oxygen plant all have one shared appetite: electricity. Making filters, pressure vessels, motors, electronics, and replacement reactor parts takes power, sometimes in brief surges and sometimes without pause. The oxygen machine also needs a steady supply of its own. Once people depend on it for breathing, fuel, and chemical work, electricity can't simply wait for better weather. A short power cut is no longer an inconvenience. It can interrupt the system, keeping the settlement alive. MOXIE made oxygen by heating Martian carbon dioxide and pushing it through a solid oxide cell. That cell worked at about 1470 degrees Fahrenheit, around 800 Celsius. Reaching that temperature takes energy. So do the pumps and compressors that move the gas, the controls that keep the reaction stable, and the cooling hardware that protects nearby parts. The oxygen then has to be checked, compressed, and stored. A larger plant would repeat those actions for months or years, rather than during a short experiment. Scale changes the role of the machine. A small unit can prove that the chemistry works. A settlement needs enough output to replace what people use, cover leaks and maintenance, build reserves, and perhaps supply vehicles. If oxygen becomes an ingredient in rocket propellant, demand rises sharply. The plant is no longer a clever box making a useful gas. It becomes part of an industrial chain tied to storage tanks, pipes, sensors, repair shops, and the equipment that makes those things. Mars offers several ways to produce electricity, though none removes the continuity problem. Solar panels can work well in clear daylight, then weaken at night or under dust. Batteries can carry power across a gap, but they add mass, wear, temperature control, and replacement needs of their own. Nuclear systems can provide a steadier flow, yet they bring demanding engineering, shielding, spare parts, and heat that must be managed. We might combine these sources, using each where it fits, but the combined system still has to survive failures without taking the oxygen supply down with it. And the backup has to be ready before the main supply fails, not afterward. That changes how the settlement must grow. Adding another greenhouse doesn't only mean more lamps, pumps, and air handling. It also means more oxygen processing and reserve capacity. Opening a metal shop adds furnaces and machine tools, then adds the power needed to make replacement parts for the power system itself. Producing fuel calls for larger reactors, stronger compressors, colder storage, and another step up in electricity. Even equipment meant to save energy may require mining, manufacturing, transport, and maintenance before it saves anything. Each rung supports the next one, while making the city more dependent on energy arriving at the right place and time. Oxygen is the product you notice because people breathe it and burn it. Behind the tanks stands a second system that must be built, expanded, repaired, and backed up at every stage. So as every larger solution climbs another rung, what invisible energy bill keeps following it? Warming Mars sounds like one task, while drilling for water sounds like another. Then come pumping, refining, compressing, storing, and shielding. The verbs seem separate because the machines are different. A heater doesn't resemble a drill, and a compressor doesn't resemble a radiation shelter. Yet each machine draws from the same power system. Translate that work into kilowatt hours, and you can see the list merge into a single demand for energy. A kilowatt hour is simply a way to count how much electrical work has been done. Run a 1 kilowatt machine for 1 hour, and it uses 1 kilowatt hour. That common measure lets engineers compare machines that have almost nothing else in common. The drill breaks rock, the pump moves water, and the refinery separates useful material. But we can add their demands to the same total. Mars then stops looking like several engineering projects placed side by side. It becomes one growing electrical bill. And the bill doesn't end when a machine finishes its first job. Warmed habitats keep losing heat. Water must be pumped again after it has been used and cleaned. Gases placed under pressure need monitoring, cooling, and sometimes recompression. Stored fuel has to remain within safe limits. Radiation protection may be passive once enough material is in place, but moving that material, repairing the equipment, and replacing worn parts still take power. A partial solution can solve one problem while adding a load that returns tomorrow. That word, tomorrow, changes the scale. A crew can spend stored energy and leave. A settlement cannot. It must produce power through dust, cold, equipment failures, and years when replacement parts arrive late or never come. If people try to alter the wider planet, the obligation grows beyond any first generation. Their children inherit the warmer ground or extracted water, along with the machines required to keep those gains from slipping away. Terraforming becomes less like completing construction and more like taking responsibility for a power system with no planned closing date. This doesn't mean every change would vanish the instant a generator stopped. Some heat could remain in soil, some shielding could stay where it was placed, and some chemical products could sit safely in storage. The whole chain, however, would not maintain itself. Every pump that freezes, seal that leaks, panel buried by dust, or reactor taken offline shifts work onto the rest of the system. Keeping the change alive means building spare capacity, then powering that too. Once all those verbs share the same denominator, the central limit is easier to see. Mars may offer water, carbon dioxide, rock, sunlight, and places to store heat, but those resources won't move or change form for free. A terraformed world would be an inheritance measured partly in kilowatt hours, paid again by people who never chose the first machines. Before they accept that obligation, where could enough dependable energy come from? Mars receives sunlight, but not with the strength or steadiness that engineers enjoy on Earth. Its greater distance from the sun means a patch of solar panel gets less than half the light that the same panel would receive near Earth. Then, the sky adds its own trouble. Fine dust settles on exposed surfaces, hangs in the air, and sometimes spreads across much of the planet. A settlement can prepare for dim days by installing more panels and storing energy. Yet every extra panel brings wiring, supports, cleaning equipment, and parts that will age in cold, abrasive dust. Batteries lose some energy while charging and discharging, and their useful capacity changes with temperature and time. Producing enough electricity across a bright afternoon is one calculation. Carrying enough through a long period of weak light is another. Nuclear power avoids the daily rise and fall of sunlight, though it brings different burdens. A reactor depends on cooling and careful control, along with replacement parts and trained crews. If one unit shuts down, the others must carry its share while people find the fault. A dependable system must therefore survive imperfect days when maintenance overlaps with damage or human mistakes. Redundancy sounds simple until you count what it requires. 2 pumps can protect against one broken pump, but both may depend on the same cable, cooling loop, workshop, or shipment of seals. A dust storm can weaken many solar fields at once. A flaw in one batch of batteries can appear across an entire storage bank. Engineers call these common mode failures. Separate machines fail together because they share one hidden weakness. Location changes the answer as well. A sunny equatorial site may favor solar power, while colder ground at higher latitudes could place accessible ice closer to the settlement. Moving electricity over distance requires transmission lines that can survive dust, temperature swings, and ground movement. Moving water or fuel instead requires pipes, vehicles, pumps, and more energy. Mars doesn't offer one best place where every need happens to meet. The result is a power network built around the worst plausible stretch, not the best average day. It needs reserve generation, stored energy, isolated backup systems, and enough spare parts to repair faults without waiting for Earth. Some equipment will sit idle much of the time because its purpose is to wake up when something else stops. That idle capacity may look wasteful on a chart. On Mars, it is part of survival. The hard limit is not how many kilowatt-hours the settlement can produce in a good year, but whether heat, air, water and food keep running through the bad week when several systems are already under repair. And if dependable power demands so much machinery before settlement can grow, what does that do to the pace and shape of terraforming itself? A larger Martian settlement might eventually build enough power equipment that no single storm, broken cable, or failed storage bank could threaten everyone at once. New reactors could join older ones, solar fields could spread across separate regions, and workshops could make replacement parts, instead of waiting months or years for shipments from Earth. Each generation might inherit systems that are stronger, wider, and easier to repair than those its parents struggled to keep alive. It could also give families more confidence that a child born there would inherit working systems rather than an emergency held together from Earth. That inheritance would change life on Mars. Reliable electricity could support larger farms, deeper water processing, warmer buildings, and factories that turn local rock and ice into usable materials. Storage could cover longer interruptions, while separate power networks could prevent trouble in one settlement from reaching another. Over time, Mars might gain a thick mesh of machines that keeps essential services running through several failures. Yet the people inside that mesh would still be human. Their lungs would need controlled air, while their blood, bones, muscles, and developing bodies would spend entire lives in gravity much weaker than Earth's. The atmosphere might become thicker without blocking enough radiation at the ground. You could live beneath a changed Martian sky and still need pressure control, shielding, enclosed rooms, and medical care. From a distance, a continent crossed by industrial sites and sealed towns might look like a planet brought under control. Inside, however, fans and pumps would still maintain life behind pressure seals and shielding. The machines could become far more capable without making our bodies less vulnerable. Even improvements to the environment would pass through this system before anyone could live by them. Collected water would still need cleaning, and warmer ground could remain beneath unsafe air. Crops might stay inside protected farms despite better soil outdoors. By supplying safe rooms and the conditions within them, the grid would turn planetary measurements into human comfort. An industrial Mars could therefore become far more secure without becoming Earth-like. Its descendants might inherit dependable power and local manufacturing, backed by stored reserves and repair knowledge. Those gains could support millions of people where a failed pump once threatened a small outpost. Still, the achievement would work around the limits of the human body rather than prove those limits had disappeared. The grid would become part of the habitat itself, as necessary as the walls around a sleeping room. If Mars can support a vast population through machinery, shielding, and controlled spaces, what would low gravity and radiation still do to people who spend their whole lives there? Radiation would remain part of life on Mars even after settlements grew rich and the air outside became thicker. Although a better atmosphere could block more harmful particles and make surface work less harsh, anything short of an immense change would still fall below the protection Earth gives a person. Here, protection comes from more than air. Earth's magnetic field turns away many charged particles from the Sun and beyond the solar system, while the atmosphere absorbs or weakens much of what gets through. Mars has no strong global magnetic field, and its thin air offers far less cover. Improving one layer of that defense would help, but it would not rebuild the whole system around the human body. Radiation would become a daily inheritance cost. Children might grow up knowing which streets had the most cover, how long they could work above ground, and when a dose reading meant it was time to go inside. Homes, schools, clinics, and transit routes could sit beneath soil, water tanks, or thick manufactured walls. People could still visit the open surface, but every hour they would carry a biological price that no prosperous city could fully ignore. The difficult part is that radiation injury often doesn't announce itself at once. A person can feel fine while damage builds inside cells. Higher exposure can raise the chance of cancer later. It may also harm the eyes or nervous system, and affect reproduction or childhood development in ways no long Mars study has measured. Astronauts and laboratories give us some evidence. No human population, however, has lived for generations under Martian gravity and radiation. Any rules for lifelong exposure would begin with real evidence, then extend beyond what that evidence has tested. A settlement would manage exposure much as a hospital handles a powerful medical hazard. It would track and limit each dose with solid barriers between the source and the body. Personal dose records might follow someone from childhood, surface crews could rotate, and outdoor work might be planned around radiation forecasts. Pregnant people and young children could receive stricter protection, while shelters for sudden bursts of solar radiation would remain close enough to reach quickly. None of this means surface life would be impossible. Better materials, buried spaces, warning systems, and medicine could reduce the danger a great deal. Some residents might accept more exposure for certain jobs or for time outdoors, while others would spend nearly all their lives behind shielding. Those choices could become part of work, housing, healthcare, and even family life. Industrial progress moves faster than biology. A city can build a covered avenue within years. It cannot quickly remake the cells of everyone who walks through it. Mars may therefore look transformed from orbit, while daily life stays shaped by protected hours, covered routes, and walls thick enough to stand in for a missing planet-wide shield. And if radiation keeps people under cover, how much freedom would low gravity allow their bodies in the places they call home? Mars pulls on everybody with only 38% of Earth gravity, a little more than 1/3 as much. Better air cannot change that, and neither can a stronger city. Such improvements alter what surrounds a person without changing how strongly the planet pulls downward. On Earth, gravity gives the body work from the day it begins to grow. Each step loads bones and muscles, helping shape living tissue through childhood. Gravity also influences circulation and balance, so on Mars, the whole body would receive a different daily signal. Exercise machines and medicines might replace some missing strain or slow certain losses. A rotating room could provide a stronger pull for a while. Yet no method has shown that decades in Martian gravity can equal life on Earth, so these measures may help without being enough. Astronauts show us part of the concern. Crews living in orbit can lose bone and muscle even while following demanding exercise plans. Mars would not be weightless, so their experience is not a direct copy of Martian life. It does show that the human body changes when its usual load falls away. Gravity is not a comfort setting that can simply be turned down. The greater uncertainty begins with people who are still growing. No human pregnancy has taken place on Mars, and no child has developed there from birth to adulthood. Researchers can study cells and animals, along with short periods of reduced gravity. Those tests still cannot show whether a baby would develop normally when the pull remains at 38% of Earth's. We do not know how the bones and muscles would form, or how the heart and balance system would work. Pregnancy adds its own unknowns. Gravity affects how fluids move and how muscles and bones are loaded. Yet no completed human pregnancy under Martian conditions can show which changes would be harmless. Even a healthy birth would answer only the first part, because growth continues for years. That gap could shape family life more deeply than any wall or airlock. Adults raised on Earth might move to Mars and accept health checks and daily training. Raising children there asks whether a body built in low gravity could stay healthy for a lifetime, and whether it could later tolerate Earth's stronger pull. A Martian city might offer sea-level pressure and warm rooms, with clean water and parks where children run without pressure suits. Yet jumps and falls would feel different, and every growing skeleton would form under a load no human child has known. The air could feel familiar, while childhood remained an experiment with no completed trial. If Mars cannot give a developing body the gravity it evolved with, what would settlers do? They might alter their bodies or build rotating homes. They might instead accept that people born there could never live comfortably on Earth. A livable Mars, then, would not be a second Earth. It could become a place where people spend less of their lives sealed behind thick walls, yet still depend on protection that Earth gives us for free. The difference is easy to miss because a city can look open long before the planet itself becomes safe. Radiation and low gravity set two very different limits. Better shielding can reduce a person's dose, and safer clothing or vehicles can extend the time spent outside. Gravity does not yield in the same way. A worker who steps onto the surface still weighs about 38% of their Earth weight, no matter how warm the air becomes or how carefully the city is designed. That makes livability a matter of degree. Early settlers might cross the surface only inside shielded vehicles, then hurry through covered entrances without exposing themselves at all. Later communities could allow short outdoor jobs during lower risk periods. Work shifts could lengthen as shelters, forecasts, and protective equipment improved. Each change would make daily life less enclosed, even if nobody could simply wander outside all afternoon. You can feel how much that would change a settlement as repair crews and scientists spent longer beyond fully pressurized tunnels. Children might enter partly sheltered courtyards, while adults worked beneath radiation-blocking roofs. Mars would begin to have an outdoors, though one governed by strict limits that differed from person to person. A necessary repair might justify added exposure for one adult, while pregnancy or a developing child would require stricter protection. Even inside the safest habitat, no engineer could promise that pregnancy and childhood under Martian gravity would unfold as they do on Earth. We have no human lifetime of evidence to settle that. So success cannot mean removing every wall or making Martian life biologically familiar. It may mean that fewer walls are needed, that people can stay outside longer, and that more work can happen beyond a sealed room. That is a real gain. It just stops short of casual surface life, Earth normal development, or any promise that a person born on Mars would share the same bodily future as someone born here. A better Mars could therefore become more open without becoming less foreign. Its residents might see the sky directly and work across larger parts of the surface, spending less time inside total enclosure. Even then, they would plan every exposure and watch every developing body with care. The planet would be more livable because freedom had expanded, not because the limits had disappeared. If that freedom arrives in stages, which parts of outdoor life should settlers try to claim first? The first rung may belong to microbes. Some could live in protected soil, beneath translucent covers, or inside shallow pools where heat and pressure are easier to hold. They would not make Mars breathable, but they could begin doing small jobs beyond the main settlement, releasing nutrients, breaking down waste, or helping prepare soil for later plants. Crops would come next, though not all at once. A plant that grows inside a pressurized greenhouse has crossed a different threshold from one that survives under a thin shelter with local Martian soil beneath its roots. Each change removes part of the enclosure. The crop may still need added water, warmth, and protection from radiation, yet its growing space can spread farther from the machines that support human lungs. That difference becomes important because plants tolerate conditions people cannot. A field might survive in air too thin for a person to breathe and at pressure too low for the human body to remain safe. If you saw green fields from a distance, Mars might seem nearly transformed. Up close, the farmer would still be wearing a pressure suit. The next rung is outdoor work with lighter equipment. If local air pressure rises enough, a damaged suit may stop being an immediate emergency, even though the air still lacks enough oxygen. Workers might trade rigid pressure suits for flexible clothing, breathing masks, and protection against cold and radiation. Walking, repairing equipment, and tending crops would become less exhausting. A mask is not the same as an open face, but anyone who has worked inside a stiff suit would feel the difference. Higher still is an atmosphere that supports breathing through a mask without added pressure. Reaching that point would widen the safe working area and make rescue easier, especially far from the nearest sealed shelter. People could move between shelters with less equipment, while homes and clinics would still control their air closely. Children, older adults, and anyone with heart or lung problems might remain inside more often than healthy workers. One planet could offer several levels of freedom at the same time. Only much later would people approach unassisted breathing outdoors, and even that would not settle every problem. Air can contain enough oxygen while remaining cold, dry, dusty, and poorly shielded from radiation. You might breathe without a tank, yet still need protective clothing and strict limits on exposure. There is no single morning when Mars changes from hostile to finished. So settlers would have to choose which rung earns the effort first. Should they favor hardy life beyond the walls, broader crop space, safer suit failure, or outdoor work with masks? Each one changes daily life, and each leaves a different limit in place. Once those choices shape whole settlements, who gets to decide which kind of freedom Mars is built to provide? The first living systems beyond a settlement's walls would probably look less like nature and more like equipment that needs feeding. A patch of algae might help process wastewater. Lichens or microbes could work inside covered beds, changing local soil chemistry. Plants could hold moisture in a sheltered growing trench where pumps, heaters and sensors still do much of the work. That may sound less impressive than a green valley, but it would be a major change in how people live on Mars. Life would no longer stay sealed inside one farm module. It would begin spreading through the settlement's support systems, taking on jobs that machines once handled alone. That changes what a settlement can safely attempt beyond its walls. A greenhouse already shows the basic partnership. Crops turn light, water and carbon dioxide into food while releasing oxygen and water vapor. People provide warmth, pressure, nutrients, pest control and repairs. Neither side runs freely. The plants support the crew, and the crew keep the conditions that let the plants survive. Over time, those partnerships could become more varied. Fungi might help break down plant waste, while bacteria recover nutrients before they are lost. Tough ground cover inside a pressurized courtyard could slow evaporation and keep dust from rising whenever someone walks through. You might notice only a cleaner path or a steadier harvest, yet many small gains could make food production more reliable and recycling less wasteful. Some living systems might eventually extend into partly protected spaces beyond the main buildings. They could sit beneath clear covers inside shallow tunnels, or behind wind barriers that reduce radiation and temperature swings. Mars would still be doing its best to freeze and dry them. Their survival would depend on human-built shelter and regular attention. So an ecology on Mars wouldn't begin as a wilderness that takes care of itself. It would begin as a working relationship, watched closely and repaired when something goes wrong. A failed pump, a harmful microbe, or a shift in soil chemistry could still damage the whole arrangement. Living systems can absorb some changes, but they can also create new ones. Biological growth would widen human choices without making Mars independent of human care. Settlers might gain larger food areas, better recycling, more stable indoor climates, and pockets of ground where helpful organisms can persist. Yet every green space would still rest on pipes, covers, stored heat, careful testing, and people who know when to intervene. The first Martian landscapes may be gardens with maintenance schedules. They would be alive, but also designed, limited, and tied to the settlements that keep them going. If people can build these partnerships well enough to spread across Mars, when does a managed living system become a world with a life of its own? A world with a life of its own may still need people. Forests on Earth are shaped by fire, climate, animals, and human hands, yet we don't dismiss them as machines. Life can be both tended and alive. On Mars, the balance would sit much farther toward tending, perhaps for centuries. The question isn't whether people can walk away from every pump and greenhouse. It's how much freedom each living layer gives to the people who inherit it. That freedom might begin with a child crossing a broad covered valley without wearing a pressure suit. The air may still be controlled, and the roof may still separate that valley from the thin Martian atmosphere, but the child could run farther than anyone from the first settlement ever could. There might be soil underfoot, insects among the plants, and enough room for weather of a limited kind. Not Earth weather, perhaps, but drifting clouds, damp mornings, or a light rain produced inside a protected region. Later generations might travel between settlements through larger sheltered corridors, or spend weeks in landscapes supported by living soil and local water. Some people could tolerate those places more easily than others. Bodies shaped by illness, age, pregnancy, or simple genetic difference would not all receive the same freedom from a changed Mars. A place that feels open to one person might remain dangerous to another. So the reward cannot be measured by one final day when Mars becomes Earth normal. There may never be such a day. Much of the planet could remain exposed to radiation, deep cold, low pressure, and dust that finds its way into almost everything. Even successful regions might depend on barriers, medical support, and constant repair. Mars could offer more life without offering unlimited life. Still, more is not a small result. More sky overhead means less time inside narrow rooms. More range means families can move, work, and visit without treating every trip as an expedition. More biological support means food, air, water, and waste can pass through systems that heal some damage instead of waiting for a replacement part from a factory. Across generations, those gains would change what a Martian childhood feels like. The first settlers may leave behind sealed rooms. Their descendants may add courtyards, then linked habitats, then valleys where many species live together. Each generation inherits a rung that someone else built and tries to add another. Success would be the growing distance between a broken machine and a human emergency, the growing number of places where a person can breathe, and the widening share of Mars where life has some room to recover. The measure would be practical. How often life can continue after a fault, and how many choices remain open when help is far away. If Mars is judged by those inherited rungs rather than by complete transformation, what should count as success? Success on Mars may look less like finishing a world and more like passing along work that still functions. The first crews won't live long enough to see every result of what they begin. A power system might serve people who weren't born when its first parts arrived. A tunnel mapped by one team may be repaired by another team's grandchildren. The project becomes a relay, except the baton is made of machines, records, skills, and trust. That changes the central engineering problem. Building a strong habitat once is hard, but keeping it understandable and repairable for a century is a different kind of work. Parts wear down. Software becomes obscure. A material that seemed permanent turns out to crack after years of dust and temperature changes. If later residents can't diagnose those failures, impressive hardware becomes a sealed box they depend on but no longer control. Maintenance habits would have to survive with the equipment. People would need to record why a pipe was rerouted, which replacement worked, and what warning appeared before a pump failed. They would also need time to teach those details. A settlement can own shelves of manuals and still lose the knowledge held in practiced hands. You may have seen a smaller version of this when one person leaves a workplace and everyone discovers that an important process lived mostly in that person's memory. Institutions carry that memory beyond any single life. They train new technicians and decide where scarce parts go, while creating routes for bad news to travel upward without being hidden. They also preserve testing routines that can feel tiresome during calm years. None of this has the appeal of a first landing, yet a city able to launch rockets can still remain fragile if it loses its maintenance culture. Inherited infrastructure also needs room to change, because its first designers cannot know every future need. If later residents cannot alter an old design, they may end up surrounded by equipment they fear or are forbidden to touch. Good relay work instead leaves replaceable sections with clear connections, supported by records that explain earlier decisions without making them sacred. The Mars project only lasts if partial wins outlive their makers. A long-running machine may carry life farther than a heroic build no one can maintain. And the same is true of schools that teach repair or councils that protect upkeep. Reaching Mars is the founders' achievement. Their descendants need working choices instead of emergencies. Even then, each generation must decide whether an old system deserves preservation or has begun to hold the settlement back. Mars would depend on continuity, while living there would require freedom to revise what was handed down. After 10,000 years, a successful Mars may still look unmistakably like Mars. The sky remains thin and dusty, the air outside still cannot be breathed, and exposed water does not stay liquid for long. Success does not require turning the whole planet into another Earth. It means life has spread beyond a few vulnerable settlements, while each new home depends less on supplies or instructions sent from far away. Some valleys might hold linked towns beneath broad roofs, with farms, workshops and wetlands sharing managed air. Elsewhere, smaller shelters could sit inside lava tubes or under layers of ice and soil. Engineered mosses, microbes, insects and food plants might take over some work once done only by machines. These living systems would still need tending, yet they could recycle waste, rebuild soil, and recover from small failures without waiting for a replacement part. Outside would become less hostile in limited places. You might work for hours in a light pressure suit, with nearby power and shelter making a longer trip possible. Distant work sites could then spread beyond the oldest cities without sharing one narrow defensive line. A bad season would remain dangerous, but more of Mars would be usable for longer, even though it was never as open as Earth. The larger change would appear in what people no longer had to import. Martian factories could make the equipment needed to expand production, while farms supplied most food and protected reserves guarded against crop loss. Communities would still depend on one another, yet a missed shipment from Earth could become a delay instead of a threat to everyone's survival. This patchwork might include places built by different cultures, using different housing and different engineered ecologies. One region could favor buried cities with small surface farms. Another might build enclosed basins where children can run beneath a roof so broad that people rarely notice it. Between these inhabited areas would remain cold deserts, steep volcanoes, and huge stretches of land with no permanent human presence. That is a Mars made easier rather than finished. More people can live there, more work can happen outside for longer, and more essentials come from local ground, water, sunlight, and skill. We might never see its people breathe the open air or stand beside an uncovered sea. They may still judge their success by something quieter: how many ways they have learned to live well beneath a sky that remains fully Martian. Mars could gain more freedom from Earth and still remain fragile. The weak point may no longer be a machine, a fuel, or a missing chemical process. It may be the chain of people and institutions responsible for keeping inherited systems alive after their builders are gone. Machines can be repaired, but someone must keep deciding that repair deserves time, training, and scarce material. That choice sounds simple until it competes with everything else. A settlement may need replacement parts for a water plant, while families want larger homes. Growers need more power, and leaders favor projects that show results before the next election or transfer of authority. Maintenance rarely has a grand unveiling. When it works, the reward is that nothing terrible happens, which makes another year of neglect easy to excuse. A relay across generations would make the strain even harder. Each generation would receive working systems and records built through centuries of effort, but it would also inherit wear and duties it never chose. If you were born on Mars, you might reasonably ask why distant plans should limit what your family can use today. No chemical formula can answer that. A durable Mars would need ways to share sacrifice without forcing one group to carry it forever. People would need trusted ways to settle disputes, teach skills whose value may not appear for decades, and change old rules when conditions shift. Too much rigidity could trap them inside failing plans. Too little continuity could allow vital knowledge and reserves to disappear during a few careless generations. We have never tested such a culture under Martian limits. Human institutions have lasted for centuries, and a few traditions have crossed much longer spans, yet societies have also broken, forgotten hard-won knowledge, drained their surroundings, and chosen immediate relief over distant safety. Mars would offer fewer escapes from those mistakes. A failed government might be replaced within years. A lost reservoir, a damaged soil system, or an abandoned chain of technical knowledge might take generations to restore, if it could be restored at all. The lasting achievement would not be a finished planet. It would be a civilization able to renew its reasons for restraint among people who never saw the first landing and feel no personal debt to Earth. Stewardship would have to feel less like obedience to the dead and more like care for living neighbors and children not yet born. Laws could support that choice, schools could preserve the necessary skills, and public customs could give it meaning, but none could guarantee it forever. Whether any culture can keep choosing repair over exhaustion and patience over short-term extraction across thousands of years, remains the deepest uncertainty on Mars. Mars can change. Given enough time, work, and patience, people could make parts of it more open to human life. Settlements might spread beyond their first sealed habitats, while food, water, air, fuel, and building materials came increasingly from the planet itself. Each gain would reduce the need for supplies from Earth and give later generations more freedom to decide how they wanted to live. None of that would turn Mars into Earth. A person standing beneath its sky would remain on a smaller world with foreign limits, living within conditions shaped by engineering and by the planet beneath it. There could be more life, more freedom, and far more land in use, while the systems protecting that life remained woven into each day. The achievement would still be real. It just wouldn't end with Earth remade in another place. The descendants from the opening would know this changed Mars as home. They might walk through valleys their ancestors could enter only in pressure suits, then return to towns built with local stone and metal. Children might inherit rivers, farms, or forests created through work begun centuries before their births. They would also inherit pumps, radiation shields, repair skills, laws, and shared duties whose failure could reach into every home. Their surroundings would feel natural because they had known nothing else, even when much of their safety had been built and maintained by human hands. The long timescale becomes awkward in a very human way. No founder can supervise a plan that lasts thousands of years. The people who begin the work won't meet those who finish it, and the people between them may decide that finishing was never the right goal. A lasting relay would have to carry knowledge through wars, migrations, changing governments, lost industries, and generations that wanted to spend their lives on something else. We don't know which technologies, customs, or institutions could keep such a relay working for millennia. We also don't know which path would cost less. Making wide regions of Mars livable could consume vast amounts of labor and material, while sealed settlements might become comfortable enough that changing the whole planet no longer seemed worthwhile. New technology could shift that comparison. Scarcity, failure, or an unexpected discovery could shift it again. Continuity means more than keeping old machines running. It means giving future people enough knowledge and capacity to change the plan without losing the world already supporting them. Mars doesn't have to become a second Earth for human life there to deepen and spread. It could become more alive in a limited but meaningful sense, inhabited across many generations, supplied increasingly from its own ground, and covered with places where living systems endure because people keep caring for them. Its foreign limits would remain, though their hold on daily life might slowly ease. Long after Earth's first crews survive only as names and recordings, their descendants may look across ground altered by countless hands and feel no contradiction. The air they breathe might pass through systems older than their grandparents. The soil beneath a farm might contain the work of people whose language has changed or vanished. A forest could seem ancient to a child, even though every tree began with a deliberate choice. Mars would still be Mars, and it would still be home. Its people would not inherit a finished planet. They would inherit a living arrangement between human needs and a world that never promised to meet them. What they passed onward would depend less on completing the work than on caring for enough of it for long enough that another generation could wake beneath that unfamiliar sky and continue living there.